imaging. It is such a pleasure to see so many people still here, even though it's a Saturday, even though all flights out of Pittsburgh pretty much terminate around 4 p.m. So I'm impressed. That's wonderful. First thing I have to do is report back on last night. I promised to stay there till the last soul went home. And I'm very pleased to say the Participatory design workshops were a total success. Just to give you an example of that, at 11 p.m., I took 2 full busloads and 14 people each back to the hotel. And then we had another busload at 12:30 a.m. So congratulations to those who stayed long, and congratulations to the rest of you who are here who didn't stay long. That's excellent. There's another kind of thanks that I wanted to do today. I didn't cover this last time. I'm trying to measure things out. And that's thanking the corporate and philanthropic sponsors that we have on the project and explaining their relationship to us. So first of all, the Farm Foundation. We've already talked about the Farm Foundation and how they are really the ones who started the entire Outreach for Science project portion of this entire thing. So we have recognized them in the past, and I thank them again. We also have in your program a set of sponsors. Gigapan Systems is a sponsor, and we are very appreciative of their work. I don't know if Henry Hillman is here. He's the CEO of Gigapan Systems. And he has taken a big risk by taking on the funding and the manufacturing of all the hardware devices, and then enabling us to make it available at a very low margin to all the educational and research uses that you all put it through. So I'm very thankful to Gigapan Systems. Google Corporation has Starkwerk funding the technology development underlying everything that we do. And so that's called gift funding coming from Google, enabling us to try and push the frontiers of gigapixel imaging in general. NASA is a corporation, is an agency with which we have a fantastic long-term relationship, and it's a pleasure that we're going to have a keynote speaker from NASA here today. And the relationship with NASA is long-standing. It includes a Space Act agreement, which is really exciting, where Carnegie Mellon's Create Lab and NASA have an agreement to work together on open source developments. Intel Corporation was a corporate sponsor that actually gave us gift funding that helped make this very thing possible. And of course, Carnegie Mellon University has helped in printing and logistical organization, running the registration, and running the website for the conference itself. And then we have 2 interesting sponsors, AAAS and IEEE. What's interesting about that is I don't know how many conferences there are that are co-sponsored by IEEE, the electronics folks, and AAAS, the science folks. I don't think that happens very often. So that I thought was really exciting. Maybe next time we'll have the National Academy of Sciences and the National Academy of Engineering. That can be our stretch goal. And then lastly, on the bottom, we have Vista Printing and Fruland and Bose. Vista Printing is very special. They were under very critical time duress at the very end, able to print out those lovely Gigapans you've seen both in Rangos upstairs and at the Museum of Natural History in the gallery. So those are all the people that are sponsoring the conference, and I'm very thankful to all of them. We're now going to introduce our keynote speaker, a 3rd and final keynote speaker for the conference. Again, it's a pleasure to have had keynote speakers from National Geographic, Google, and NASA. That was a dream come true for us. To introduce our keynote speaker, I'm going to present to you Philip Lehman, who is Associate Dean of the School of Computer Science.
Thank you, Ella. Glad you're all here. So welcome again to the 3rd day of the fine International Conference on Gigapan Imaging for Science, and to the Rashid Auditorium, the Gates Center for Computer Science, and the Hillman Center for Future Generation Technologies, proving that we really like long names around here. These buildings were opened last fall, just a little over a year ago. It's a new home for the School of Computer Science. And one of the goals is to continue to build the interdisciplinary collaboration for which Carnegie Mellon is so well known. Among other things in these buildings, we work at the boundaries of computer science and the physical sciences, notably including biology and cosmology as we walk around. So this is exactly the perfect conference to house here. As Ella mentioned, I'm Philip Lehman. I'm really delighted to be able to say a few words about the valued partnership with NASA and about this morning's keynote speaker, Dr. David Korsmeyer, who's Chief of the Intelligence Systems Division at the NASA Ames Research Center, also a long title. I want to talk about the relationship with NASA. We have a number of multi-year initiatives with NASA, giving scientists access to both the resources of Carnegie Mellon, which is, as you know, one of the world's leading research universities, and NASA, an agency that, well, for most of us, actually literally needs no introduction, since their work really inspired many of us, including me, to become scientists in the first place. The Ames Research Center is, I think, its largest research and development center in advanced software and really central to all of the NASA missions, right? So, sorry?
We like to think so.
They like to think so. And as it happens, NASA is also home to Carnegie Mellon Silicon Valley campus on the West Coast, so it might be said that we've moved in together. I don't know if our parents know, but so the partnership enables Carnegie Mellon and NASA researchers to work on technology cooperatively. For example, Gigapan is a great example of the results of the collaboration. In fact, it began when Randy Sargent and Illa were working at NASA. At the time, I think Randy was a technical staff member at Ames and was developing software for combining images. And Illa was on sabbatical from here, if my history is correct, leading the intelligent robotics group there when the idea for Gigapan was really developed. And provide details later. Many other projects have resulted from this partnership. For example, we've worked with NASA to explore the world's deepest sinkhole, floor of the Mojave Desert, measure gravity waves caused by black holes colliding, which is an example of the cosmology work I was talking about, and is at the intersection of computer science, astrophysics, particle physics, and statistics. We also have a small project here that aims to do something trivial, which is send a robot to the moon in 2013. And that's part of the Google Lunar X Prize competition. And NASA recently awarded that team a contract through their Innovative Lunar Demonstrations Data Program for data to be gathered during that little jaunt. Gigapan is really a perfect example of the hallmarks of Carnegie Mellon that President Cohen likes to talk about. Problem solving on real world problems, interdisciplinary collaboration, innovation, and frankly, hard work. So the partnership for Gigapan with NASA, Google, and National Geographic really embodies our ideals of outreach and engaging the community and advancing the goals of science generally. So the possibilities, for me anyway, for science, education, outreach, and excitement when you think about what you can do with Gigapan and space, totally mind-boggling. I don't even claim to begin to address them. I think that's actually your job. So that's why I'm so excited to be introducing David. Over the past 20 years, he's served in several senior program roles across the agency, supporting both robotic and manned spaceflight. Recently, he was the lead of the Near-Earth Asteroid Mission Concept Study, long names again, for NASA's Constellation program, and supported the Human Spaceflight Review Panel, where he led the technical analysis for the flexible path architecture exploration. And I recently learned about his two most important credentials. He grew up here in the South Hills, and he's a Steelers fan. So it's my great pleasure to welcome David to Carnegie Mellon.
Thank you, Philip. If it's okay with you, I'm going to just yell. I'm a little bit more comfortable doing that. I have kids. So, okay. Again, thank you very much for having me here. I greatly appreciate it. I greatly appreciate the effort it took to get up, or Illa maybe never go to bed, to be here this morning. My name is Dave Korsmeyer. I am from NASA Ames, and I'm going to talk about a piece of NASA's activities. I want to do due diligence and note that NASA stands for National Aeronautics and Space Administration. Aeronautics, the little a, I will not talk about. It is important. We do really cool stuff there. And space, I'm going to talk about both robotic and manned space, but space, the up and out, not the down and in. We also do a lot of space earth science. Not going to talk too much about that today. So I'm just going to give you a little bit of a venue of what's going on and how we're using kind of gigapixel imagery in general to do our exploration. First, just a little synopsis. NASA Ames. Well, that sounds interesting. Why say NASA Ames? Why not just say NASA? NASA actually has 10 centers. Some people don't know that, so I'm giving you a little quickie here. Located around the country. The one that I'm most fond of is NASA Ames. We're basically, they like to say, in the heart of Silicon Valley. It means at the bottom of the San Francisco Bay. Okay? Stanford's across the way from us. Google's right next door to us. UC Berkeley's across the bay. We have all sorts of cool stuff here, and you know, right on our site here, right about there, is CMU Silicon Valley, right? So they're actually on our facility. So when we talk about actually being jointly connected, that's what we're talking about. So that's the research center I'm talking about, and one of our key areas of interest is in computer science and information technology. Ergo, it makes sense to do stuff with CMU, as an example. So let me start with Mars. Why am I starting with Mars? Well, in some sense, it all started here for Ela and Randy and Anne and Matt Deans and a number of other people, because we were supporting a rather popular little Mars rover set, Spirit and Opportunity, which landed on Mars January 4th, 2004. And Ames was tasked as part of the NASA team to work on the imagery that was coming down from these PanCams, which are, this is called the Mast and the Boom and the panorama cameras. And, you know, it's a kind of a clever idea. It's a little fancy high-res digital camera that's on a robot, and it moves ever so slowly to take a picture. Perhaps you've heard about it. And so we were taking and dealing with all that data, and we created, not me, but we meaning really Randy and his team under Ela. And I'd like to point out that Ela's on sabbatical from Ames to CMU, just to make sure we understand each other. So we developed this the MER image browser as one of our tool sets, and we were dealing with the data and playing with it. And soon into it, we started developing some particular software that allowed us to very rapidly stitch together some of the images, a little less rigorously, you might say, than JPL's rather arduous task of perfectly aligning every pixel. But we wanted to quickly kind of look at the data and assess it and drill into it and see what was going on. And so, you know, you can see here, this is actually at the landing of Spirit. The pod's kind of opened, you know, the starseed's coming out, and we're getting the panorama, and oh, it looks kind of interesting. We see some stuff here. And the software, if you notice, we're going to zoom in on this point here. You know, the software allowed us to kind of zoom in amongst these tiled images, and sure enough, we're looking for a rock outcrop, and that one looks really good, so we're going to zoom in again, and ooh, that looks like a really nice rock outcrop, and we zoom in again, and lo and behold, you know, those doggone geologists have been looking for bedrock, and there it is. We didn't even roll out, and we got it. And we got it really quick, and we got to be able to tell the science team, go look with your really high res, go there and do your scratch and sniff, because that's the most important thing. Now, what came from this is Randy and Larry Edwards and Matt Deans and Anne Wright, and all working at NASA Ames, all working in Ela's group, they developed this stuff. They were playing around with it and thought, well, this is kind of cool. We should really do more things with panoramas, because panoramas are really kind of neat. And correct me when I'm wrong here, Ela. You know, we really like this stuff, but let's start seeing if we can do this with maybe the then up-and-coming digital cameras. You know, you remember these. That was when they were 2 megapixel, and they cost a couple $100, or, you know, they really weren't the type of SLRs we have today. And so we developed a first cut at this software, and Randy was careful to point out that JPL produced the actual official products, and, you know, but we produced the really cool ones. So they got together and talked about, is there something we can do low cost that can allow us to make this technology available? And they came up with an idea of a thing called Global Connection, which is the agreement we've got in between CMU. And if you go back and you look at some of the early prototypes, I think this was mounted on the outside of somebody's house. Yeah. You know, it started just in August, so several months after the Mars rover landing, gathering pictures, and it gathered stuff like this, right? You know, and that's a nice backyard. And so, you know, that's from whence some of this comes, just to give you a little context from our perspective. And now the Global Connection activity, which is, you know, a partnership of CMU, Google, National Geographic, NASA, is going on, Gigapan.org, you know, providing these very inexpensive, within the NASA context, virtually free robotic systems that allow really participatory exploration. So going back to NASA again, what has changed for NASA since Apollo era, right? Everybody knows the Apollo era, you know, boots and suits on the moon. Well, we've got a lot more orbital assets. We've got a lot more computational technology allows us to do simulations. We've been to actual other planetary surfaces beyond just the moon, and we have very advanced robotics capabilities now. Well, gee, that's, okay, is that different? Does that change things? Well, yeah, it does. So if we look at some NASA exploration targets, and I'm going to take you through a little bit of the inner solar system. Again, I said I'm constraining things, and for those of you that don't know, this is not to scale. And this does represent our solar system. So, you know, here's us, here's the moon. We're going to talk about Mars, we're going to talk about near-Earth objects, and we're going to talk about the asteroid belt a little bit. But those are areas that we're looking, believe it or not, at both robotic, obviously, and manned exploration. You know, those are our targets. We're not going to go out to the main asteroid belt anytime real soon, but we'll talk about it. So going back to Mars a little bit, what's our next step? As I was talking to people at lunch, you know, there was maybe not a common understanding of our plan, because NASA barely has a common understanding of our plan, because this is actually pretty recent. We just cut a deal where NASA and the European Space Agency have agreed to a joint Mars exploration investment program, which is really good. Because the Europeans do some wonderful stuff, and so we're combining investments and combining vehicles and systems, and we've got some wonderful things in the out years. I'm not going to talk too much about that, but I am going to talk about this one, which is called the Mars Science Laboratory. So we have the MER rovers, which, as many of you know, and I just stated, landed in 2004. You know, and it's like Gilligan's Island. You know, they were there for a 3-hour tour. These were there for a 3-month tour, and they never left, right? So they're still there. They're still operating. One of them's dug a hole for itself, and it's just kind of sitting around. The other one's still moving. And, you know, that's one of our best investments ever, right? This Mars exploration rover. So we're following it up with the Mars Science rover, who has not much to live up to, but it's the bigger, badder brother of the Mars rover. So where, you know, you can think of this as a golf cart, this is more like the Humvee, right? That's what they're shooting for. And, you know, it has all the right words, right? It's nuclear powered and, you know, really big and beefy. One of the key things here is, again, we're going to have one of these masts and robotic cameras, and lo and behold, you know, it's called a MastCam, and we're going to use it to take big panoramas. We're going to use it to take big 3D panoramas. And we're going to use it to take something that we haven't done before, which is not often noticed. We don't take video. Has anybody noticed that? NASA does not take video. We do it in low Earth orbit, don't get me wrong, but we've never taken video on another planet. Why is that? Well, because video tends to be much, much lower resolution. The technology really wasn't there. You know, you could bring back a canister of film, but, you know, if you wanted to take a high definition video in the past, it had to be, you know, photographic plates. It was not something you could do, and you just couldn't pull the image, the data off the pixel, off the CCD quick enough. Right now you can. That's common technology. Right? You've got these HD cameras that you can buy. So NASA's basically flying one of these. I think it's 5 frames per second at a high res and 15 frames per second, we think, at a lower res. So we're actually going to have the ability to actually capture dynamic information on the surface of another planet. I think that's tremendously exciting at high res. Right now we take snapshots as quickly as we can, and we kind of compost them together and run them and hope nobody notices. But it's not video. Okay, so going from Mars, where we're going to have some really cool camera imagery, how else is NASA using images to explore? Well, I want to give you a little bit of a step through here, just so that we are all on the same page. When I'm talking about where else we're talking about going, one of the places is an asteroid. Now, to be specific, I'm talking about what's called a near-Earth asteroid. And what I mean by that is its orbit around the sun is in the vicinity of the orbit of the Earth. And they align every now and then so that it's relatively close, 10, 20 million miles. Okay, about 20 to 40 times the distance between the Earth and the Moon. Okay, so that's close in our land. But when we're talking about the scale of the object, right, here's the limb of Mars. Here's a main belt asteroid series, which is really kind of a microplanet. Here's Vesta. We're actually sending a mission to those now called Dawn that will get there in the next year, and we'll get some much better than these blurry images. There's a small rock here called Eros, and a mission called NEAR went to that, as it was a NASA mission, and it looks like this when we got up close. And that's kind of like the best imagery we have of it right now, to be quite candid. And then the Japanese sent a really fabulous one to a small rock, and these are to scale. I didn't just lose the image. That little thing down there is Itokawa, which is another near-Earth asteroid that the Japanese went to, and they're very proudly showing their data. And it looks like this, kind of a weird broken peanut. Now, just for scale, this is the biggest thing we've ever built in space. And this little thing is, you know, the Orion spacecraft, which kind of looks like a fat Apollo spacecraft, right? So if we're talking about sending a manned mission to an asteroid, this is a baby, and this is what it would look like, okay? Now, the Japanese, the mission was called Hayabusa, the spacecraft was called Hayabusa, that went there. They collected some really fabulous data. And again, remember, NASA and most of the other spacefaring nations, when we talk about exploring in space, we explore in pictures. We have no choice but to explore in pictures, because how else are we going to do it? You know, it's some visible spectra or some spectrum that we then map back to a visible spectra so that we can understand it. We're visible creatures. So if you look at the neck in between here, the neck part in between the two lobes of this kind of weird potato-shaped asteroid, they were looking for a good place to actually do a sample where basically the spacecraft was going to fly, bump into the surface, and then hopefully some particulates would come up. They would close a little latch and they'd fly it back. And they have indeed limped back to Earth. They did a fabulous job getting home, but we don't know if there's any samples yet. But they were targeting this, and they were looking at all these various outcrops, and you can see how flaky it is, right? The lighting is very weird. It's a rubble pile, basically, is what it looks like. So what they got is they got limited imagery as they were going in. You know, at 80 meters, you could see this. Here's the kind of meter scale bar. And this is, you know, the PowerPoint experts Gigapan. The 68 meters, and then at 63 meters, and then at touchdown. And so this is, you know, kind of pebble size, small almond sized gravel that's there. Now, one of the things that they're doing is they're actually attempting to put this into full mosaics. They haven't got there yet. We're trying to negotiate to get access to some of the data to allow that to occur. But you can see, and they're also going back, I should be careful to say, they're going back with a Mark II of the Hayabusa to a different asteroid. And this time they're taking basically, you know, megapixel class imagery systems with them, particularly to basically do a full mapping of the actual asteroid. So that's the type of exploration we're doing on the asteroid. And the idea is, you know, eventually you'd send a human mission to one of these things to do, or a much more robust robotic mission to do a significant sample return of up to kilograms of things. So when we talk about mapping a planetary body, that was a planetary body. And some of the other things we do, in particular at NASA Ames, is we're looking at how to create these planetary maps using kind of derivatives, if you would have it, of the same software and techniques that you use for Gigapans. How do you create these high-quality digital maps? How do you enable quick, easy access? Some of that's already been, defined by the gigapan.org structure. How do you provide very rapid updates? We get lots of data, and we want to create these 3D terrain reconstructions from these images. And we want to provide it in kind of open data sets that everyone gets access to. We're the government. Believe it or not, we're here to help. But in truth, from the NASA perspective, come on, what harm can we do? We're here to basically provide the forefront of exploration into areas that we otherwise can't get access to. That's what we do. We might as well make the data available for everybody because you paid for it. So one of the key problems or challenges for us is that more and more and more data is coming back. That's a good thing, but it's also a challenge, right? When we talked about going to Mars with some of the first orbiters, this is Mars Global Surveyor, we got a little bit of data. And then we sent out another one, Mars Odyssey, and then we sent the MER rovers, and they're gathering a lot, but they're gathering a lot more than we thought because really they've been there so much longer. We sent out what's called the Mars Reconnaissance Orbiter, which was a class of orbital satellite that you would have for doing imagery on the Earth. So it's the same class of imagery system that you use for doing remote sensing on the Earth. We sent it to Mars, and they've given us a big block of data. The Apollo imagery, you may remember, was not digital back in the analog age, but they took tremendous photographic historical records that we're now actually digitizing and using that information. And then, Selene and Chang'e 1 and Chandrayaan, other countries, Japanese, China, and India. And then our own LRO, which is the Lunar Reconnaissance Orbiter, which is there now and has done a full map at very high resolution of the moon. And we're actually compositing all that data together. I wish I could show you that. I can't show you that right now because it's unreleasable. But we're playing with it, which is nice. So this gives you an idea of kind of the magnitude in a different manner of the fire hose we're dealing with, right? Cartography has traditionally been map making has been a human activity, right? Because it's how things relate to each other. It's been very manual. We work with USGS, the kind of the greatest map makers in the world. They hold the NASA, well, they hold the US government's imprinteur for having the maps of the universe, right? So you want to know where something is on the Earth, you go to the USGS, and they'll tell you where it is, and it's here related to this, related to some central point. If you want to know the map of the moon, guess what? The US Geological Survey Service still, even though it says geological, they hold for other planetary bodies. They're the same one for the moon. It's likely they will expand that domain to other planetary bodies, but right now for the moon, they're it too. So as we gathered the Apollo-metric data, they'd created a lunar body representation. On Mars, we're collecting data, lots and lots of data on the lunar update that's now going into that system. Even tremendously more data, and we're scanning, years of high-res digital film from the past Apollo-era experiences that we've got. And the way we do that is it's a transect Gigapan. That's what it is. It's the same thing. You're just moving, taking a picture, you're knowing where you are, finding the overlaps, and again, they're pictures, not videos, and then building the appropriate panorama. And with parallax, you're allowed to get out the depth, and that gives you basically the geography, right? So that's a problem, though, because that's a technical challenge, and when NASA Ames and CMU and others are working on open source packages and common languages that we're making available to other universities and to academics and industry to go off and do great things with, that we're using to basically pull out the 3D contours, the 3D surface maps of these other planets, of these other places, and make them representable and actually put them on sites like Gigapans so that people can consume and use them. Again, the acronyms, the National Acronym and Space Agency, I said. We have lots of them. Just trust me, that's one camera, that's another camera, and that's another camera. And you know, we're able, with the different cameras and the different information sets, but with the same software package, making it very general, to pull out these nice surface topographies. And we're doing that for Mars, and then we're basically integrating these various topographies to give you the best of the breed, right? That's what you're really trying to get. And so there was a really nice talk about how you align Gigapan images. Well, just imagine, right? You know, this is the same idea on a big scale. How do you do that? That's a nice challenge. This gives you an idea of a very nice Mars terrain where you get some very good surface definition. We're down to 5 meters per pixel. So it's at a pretty high resolution. And that's the type of information we want to have so that when people go to Mars, either virtually or physically, they will be able to explore and really understand the context of what's going on. You know, the speaker from Google yesterday said, right, a picture is worth 1,000 words, right? A Gigapan's like a novel, right? There's just lots and lots and lots of things you can go through time and time again. So same way we did it for Mars, we're doing it in a bit of an inverted scale for the moon. For the first half, instead of taking a picture of the moon, we're taking a picture of a picture, right? We're scanning the film assets from the transects that the Apollo spacecraft did over the surface of the moon with their very high quality photographic, chemical photographic systems. And then pulling out these image maps and creating these surface topographies and sharing that. And then we're basically, with USGS, we're mapping them back onto the actual archival, you know, pristine, idealized lunar map. And we've got a thing called the Lunar Mapping and Modeling Project that's doing that. And, you know, just to give you an idea, you know, when they went to the moon, they had this very nice camera here, this Apollo mapping camera. And you can go to this site where there's the archive of the digitized version of a lot of the images, and they're being restored and being properly correlated. And then we're using that raw material and putting it all together. So, like I said, we're basically taking what were separate snapshots and doing a big transect and creating a big Gigapan. And that allows us, a big 3D Gigapan, and that allows us then to overlay these things so that, you know, you've got the kind of the traditional moon imagery that you've pulled together, wrapped around the globe, and now we've got a very high resolution swath of what's going on. And you know, we've geotagged it, quote unquote, with all the appropriate craters and all the cool stuff that's going on. And we're down to, you know, nice 10 meters per pixel, only 80 images. But what's coming soon for Mars is we've got that really fine, high, and it's called high rise, and it's, you can guess, it's high resolution, very nice high resolution system that's going around Mars. And instead of just getting, you know, a small swath from the photographic plates of Apollo and putting it on the moon, we're going to get some big, huge swaths from this very high resolution camera system that's going around Mars now and stitch it all together. Each of the tiles are 256 by 256. There's a lot of them. There's way a lot of, well, there's a lot of root tiles, but there's just 230 million full tiles. We're talking about almost 6 terabytes of data. That's going to be a Gigapan. Right? Right. That's what we call. What did you call it yesterday? The petapan, the exapan. You know, you start losing things. But that's the idea, and that's going to give you a full virtual world then, in some sense, to truly explore well before we get there in person. So how do we make this available for everybody? How do we make this something that people can get access to? Well, we want people, I mean, that's our goal. It's written in law. If you go back and you look at the Space Act that was signed in 1958 for NASA, it's written in law. We are to serve the public by making access to space and other assets and all its products available to the public. And so, guess what? This little thing called the World Wide Web came along, and we're still not that great at it. Thank God other people are. And so we're trying to get very low barrier to entry, and we're working with small groups like Google Earth and Microsoft Worldwide Telescope, and they're enabling us really to get out the material, the information, the data that we need to, gigapan.org, and allowing what is now was an original euphemism for something that was almost derogatory. Oh, citizen science is now become the true massively parallel activity of, oh my God, citizen science. You know, it's free. Post it on the web and they'll find all the hard stuff and we'll just pick out, you know, the wheat from the chaff. It'll be great. There's a lot of chaff, but who cares? Look at the wheat, right? And how much did it cost? Not much. This, I believe, is one of the most significant and powerful sea changes in the way that NASA will explore. Because frankly, if you go back, there you go, just this one. If you go back, how long is it going to take, you know, the handful of paid government researchers to go through this data? Far, far, far too long, right? We don't have the manpower. We don't have the skill. They're going to lose the desire and they're going to get old and die. So citizen science is really the way to make this happen, right? There were some good examples yesterday where they posted things on the web and, you know, days later, millions of hits have come through and they found these nuggets, these gems, these pieces. And that's a real model that we want to leverage and make use of. So, you know, like I said, if you go to you know, your Google Earth browser and you go up, you can select Google Mars, you can select Google Moon, and you can, and if you go to the Microsoft Worldwide Telescope site, you can select Mars as well, and you can get access to any number of good NASA data sets and tours so that will take you through with sometimes written, sometimes audio tours describing how the data interrelates, what you should be looking for, where there is value, and telling you more information than you probably want to know, but you have the pause button, so it works. And all of this is available through open standards, so all of this data then is usable by anybody, by any corporation, by any country for that matter, by any academic institution to learn, to understand, and to explore. So, as I said, you know, we partnered, excuse me, we partnered with Google. And in 2009, just about a year and almost 2 years ago, we released Mars 3D in Google, and we've got all this wonderful stuff. And it had the best data of the day, and we've got a pipeline now into that system where we're providing the latest and greatest as it becomes releasable. So it is available. Now, people are saying, oh, you're favoring Google. No, we're not. We'll partner with anybody who wants to sign a Space Act agreement with us, even CMU, and, you know, allow them access to the data. You know, there's some constraints that we want to be able to understand how we get it to them, and they can't go off and sell it again, but they're not selling it again. And we didn't have to develop the system. We don't have to support the servers. You know, it's a great partnership. You know, we get Bill Nye the Science Guy to give tours. I mean, and Ira Flatow from NPR. I mean, what else could you want? We also did that for Google Moon. So 6 months later, July 20th, an anniversary date, if many of you remember, for landing on the moon. And there's also these wonderful tours and panoramas. So you can go down through Google Moon, get into the system, and drop into a panorama that was taken photographically at the site that we've redigitized and contextually tagged. And so you actually have a wonderful way to do your citizen science, your exploration of the moon, at a much higher fidelity than anybody except the Apollo astronauts has ever had. Right? And roll that around in your head for a second, because it took me a minute to actually understand that. You have access to data that nobody, not even really the Apollo astronauts, had at the time. It's been compositive, it's been registered, it's been tagged, it's been synthesized, it's been geolocated, and it's been put in an easily consumable, accessible form. And you can just, I think you're on it now in the back, right? So pay attention. It's really easy to get there. That's a tremendous benefit that has come out of the partnerships we've got. Now let me tell you, in my last few minutes here, about some of the stuff that NASA Ames in particular is doing in preparation for the next set of exploration, in particular manned exploration, that's going to be happening sometime soon, we hope. But in essence, what we do is we do analog exploration activities. Why? The same way you practice piano, you want to practice exploring, right? The same way geologists learn by going out into the field to see what they're looking for as opposed to sitting in a classroom and getting a dry lecture. You want to practice your trade. NASA's trade in doing human exploration or robotic exploration is sending something out into a strange environment and seeing how well it works and seeing what it does. So we do what are called analog missions. Every summer we do these things around various locations in the country. In 2009 we did one, and we've been back to this place several times, but a particular place near the Grand Canyon called the Black Point Lava Flow. The reason we went is because it's got some really nice, the term is geomorphology, it's got some nice rock shapes, okay? And it looks like lava flows we may see on other planetary surfaces. So we want to go and test out our equipment, see how well it works against something that's, you know, an analog, right? We, being NASA, bought this very expensive Gigapan system and put it on this cheap robot. That was a joke, yeah. Actually, this is a cheap robot as far as robots go. This is the K-10 rover at NASA Ames, and it's part of a suite of instruments, and there's more, but these are the kind of the visual ones, where we put a nice scanning LiDAR system that gives you a very high resolution topographic measurements. So you can get 5 millimeter measurements at a 500 meter distance, so very fine. That's where you get your surface shapes. Literally, it's a Gigapan. It's exactly what it is. Bought, purchased, well, maybe. And it's sitting up there, and it's taking our panoramas, and then we've got a microscopic imager. And all of these can give us that full high gigapixel resolution data that allows us to explore virtually what's going on. So we take, we start with orbital imagery, go in, take high resolution gigapixel panoramas and panorama zooms that allow us to get down with the microscopic imager to even 55 microns per pixel, right? Very fine-grained zooming capability, again. But this is the type of information that then the robotic systems provide back to the controllers, the science team, to do the exploration. And there's a number of reasons you can do this for down selecting the data. The LiDAR system will give you an actual surface understanding of what you're seeing visually, geolocated, and co-referenced with the Gigapan, so that you really understand. It's not as good as being there, it's not, but it's really good. It really tells you a lot about the system, and if you're trained in the particulars of the science of geology, but then also trained in the use of these systems in the field, it becomes a very powerful and enabling capability, not for doing the Black Point lava flow, but for doing things like are going to happen on the Mars Science Lab, which is the next Mars rover I talked about earlier, that will be launching later this year and getting to Mars. So we did all this data collection, did these various recons, and geotagged the heck out of it, right? And so we ended up with, you know, a representation of a nice 8.5 gigabytes, 52 hours of robotic recon data, 39 LiDAR scans, 75 Gigapans, 95 terrain maps, right? That was our week in the field, right? And that is demonstrably the type of exploration and the type of capability that you want to enable for planetary science that we make at NASA Ames. And this is what we're going to have available and ready for us in the future. One of the other cool ways we do this, you know, this isn't just a robotic system. This is what's called the Lunar Exploration Rover. This is our play Lunar Rover that we're dealing with, and we've mounted a Gigapan system on it. It's gone off in the field. It's actually a full self-contained Gigapan system and laptop with all the software, so it does the whole package. You can just do it right there, composite them all together. And we did a whole set of citizen science with that, where, is that in my next slide? Yeah. So DRATS, it was the name of the field test, where we had this Gigapan on the Lunar Rover, and we basically, they went out, we tried out a number of things where we took just a boatload of Gigapans, put it on this site and said, you, the citizen, go out, tell us where we should explore. What do you see? What do you find? What's useful to you? And they helped inform, so we got public input into the final plan. They helped inform what the exploration would be. Where was the interesting outcrop? Where was the little widget you wanted to look? Where was the cool rock? What was the stuff you could care less about? And that was basically through the gigapan.org site. You know, we partnered with that, and that worked out exceptionally well. We got a huge number of hits. We got a huge amount of interest from the public telling us, hey, this is kind of interesting. You know, I didn't know NASA did this. This is like, you know, jamboree for roboticists. And it was. But now you allow a lot more people to join in that exploration with you. And, you know, the goal is that when we go to a planetary surface, this is, again, the type of capability that you have online for everyone to get access to. So it's not just, you know, by reading the latest newspaper, you see the latest picture, right? You actually get access to the real data, to the real cool stuff. So to sum up, basically, one of the reasons I like working for NASA, I told some people earlier this morning, you know, I'm an engineer. I'm one of those aerospace engineers. Computer science is kind of my hobby, right? Then there's the computer scientists, and space is kind of their hobby, right? The intersection works out really well in that NASA is one of the very unique organizations that we generate some of the most heterogeneous, diverse, weird data you would ever get. It just comes from out of this world. It comes literally from everywhere. And so we get these multi-scale, multi-type, multi-spectral data sets. We gather it from the micro, sometimes down to the nanoscale, all the way to the macro scale. And we want to reference it. And one of the key powerful things here is that the relative or the location context of where the images are relative to each other and to other systems tells you information in and of itself. It's tremendously powerful. It's how our brains are wired. So it's great stuff. Because of that, Gigapixel Exploration is here to stay. It may have not fully started with NASA, but we've used it exceptionally well. And we're very proud of our partnership with CMU, Google, and many others, and the citizen science citizenry, whatever that is. You people that are actually using these tools and technologies to do great science out there. This is kind of the forerunner of how it's going to be done. So I'm glad to have spent some time here with you in Pittsburgh. Thank you, Ila, for inviting me. So they are transects, and the percentage covering, do you guys know? It's a pretty high percentage of covering, so there's a lot of overlap. It basically is doing a polar orbit, And so they're taking these nice swaths, and we're trying to get as much overlap as you get. Right now it looks kind of like an unpeeled orange with little unfilled in pieces. But the longer it survives, the more opportunities it will be to fill it in and flesh that out. So it's going to be very, very high resolution data. It's very impressive stuff. I mean, you can actually see, I don't know, I didn't show any Gigapans, I'm sorry, but there are some on the site, and gigapan.org, you can just look them up. But there are images of the Mars rover lander, its tracks, and the back shell that you can see from orbit. So we're really there, or we're really faking it quite well. So. Yes, sir.
Could you talk about video a little bit? It's counterintuitive to me in the sense you don't expect some things hopping while as you're taking video.
Okay, that's actually a really good question, and I don't have a really solid technical answer. I can give you my guess. One, it was just technically challenging and hard to figure out how you were going to get video, because it's a straw in the sense of it's the straw of a connection, very thin, narrow, hard to get data in and out for long distance missions. So video, you know, and the idea of digitizing video, that's a relatively, you know, new technology in the past 20 years that's mature enough with all of the computer science that goes behind compressing everything else. So that was one challenge. And then I believe, me personally, that there's somewhat of a bias in the scientific community when we sent out the surveyors missions. Early, we looked around and we thought, you know, we were going to Mars and we were going to see the canals, and then we got there and all we saw were a bunch of dead craters. And everyone went and said, oh, it's a dead planet. Right? You remember that phrase, Mars is a dead planet. And that kind of biased people's perceptions about what type of science they would get. We're going to a static, airless world, and we just need to scratch it, and we'll be fine. And, you know, some of the biggest surprises that the Mars rover team had was wind comes in and brushes off the solar arrays on the Mars rover, and the power jumps up. Oh, there's a little dynamic atmosphere. They took a picture once, and they saw a funny whirl, and they realized it was a dust devil moving across the surface of Mars. And we ended up putting software on board the Mars rover to opportunistically capture that, and you can see a couple quick snaps of a dust devil moving. So now there's a sudden motivation of, hey, maybe things are a little bit more dynamic than we think. And so there is a desire for video, but really for technical and cultural reasons, I think we were just slow getting there.
One more question.
Oh, take it.
I'm a forensic photographer, and we have cameras that can take like 1,000 pictures in a second now that are pretty inexpensive. It seems to me that, do you have any plans of putting that type of imagery, getting that kind of imagery from Mars, catching maybe some of the dust devils and stuff like that?
So the MSL, the Mars Science Lab camera, does add up about a megapixel, 5 frames per second. We think it gets up to 15 frames per second. I wasn't sure because I was looking at old slides for a lower resolution, kind of a 800 by 600 resolution. So yeah, we're definitely flying it. And you know, the lead time between a commercially available CCD and then making it space rated, and then sitting around and waiting for the launch, and then actually it flying and getting there, means, you know, we're 10, 15 years behind on a good day, technically, right? That's just the way it is. Okay? I'm available for other questions in the hall if you'd like.
Let's thank Dave again.